All right. Hi, everyone. Welcome to our weekly developmental seminar. Today, it is my great pleasure to introduce Dr. Jonathan Park, who is an assistant professor of quantitative psychology here in our department at UC Davis. This is very cutting edge work. I'm very excited. His research focuses on avenues by which we can integrate complex systems techniques from graph theory, dynamical systems, and fuzzy statistics to improve the measurement and modeling of individual processes. His research interests lie in understanding the development of psychological disorders via the identification of subtypes of individuals with major depressive disorder and other related health conditions, and the discovery of stable, vulnerable symptoms, which may serve as targets of intervention. He earned his PhD from the Pennsylvania State University in 2024 and has been at UC Davis for 1 year. We are extremely fortunate to have him here. He's a very renowned expert in this area, and today he'll be talking to us about the classification of heterogeneous time series in continuous time. Please join me in welcoming Dr. Jonathan Park.
Hello. Do I need this for the people on Zoom, right? Okay. I don't know that I'm going to fully live up to that, but I am happy to be here and thank you all for coming. Yeah, so as Cam said, I'm a faculty member in the quantitative area in the psych department, and my talk is classification of heterogeneous time series and continuous time, which is quite a lot of vocabulary words. So throughout the kind of introduction part of this talk, for those who are unfamiliar with any of these terms or the combination of these terms, they will be defined. And if I fail to do that, please do let me know. And so this is basically a project that I've been working on for the past couple of months as an extension of my doctoral work when I published continuous time-gimme. So this is kind of extending it to deal with this idea of heterogeneity in time series. I always like to situate my talks by giving a table of contents as well as like a problem statement that talks about the things that I'm going to talk about. So with the table of contents, I will basically be talking about the motivation of this project, and that basically falls into two main components. First is this idea of modeling processes in continuous time. I'll talk about how we typically think about processes and whether our models really align with that. And basically, I'm trying to sell everyone on continuous time models. And then I'll talk about this idea of undiagnosed heterogeneity. Basically, this idea that often we're interested in finding things like subgroups or subtypes of individuals, but we might not know the exact features that distinguish groups of people from one another. So we might have a lot of data, but we don't really know what actually qualitatively separates people. And so if we can come up with ways to actually do both of these, model things more accurate to our processes, but also find or diagnose heterogeneity when we don't know the features of that, that would be quite useful. And then obviously apropos to that, I'm going to talk about cts-gimme, which is the thing that presumably will address the two motivating points because that's how I structured this talk. I'll talk very briefly about some early simulation results that I've been doing, and then an empirical illustration that I have on a sample of individuals with major depressive disorder. And then obviously I'll end it with a discussion points of limitations and implications of this work, but also really interesting things that I'm looking forward to. And let me know, because part of a lot of quantitative methods is also getting people excited about our work and giving people more sophisticated tools to answer really cool questions, right? Like I just kind of do things on my computer, and the real cool questions happen from people that are doing this kind of work. Great. So this isn't working. Let's go back. Okay. So problem statements are basically these big points that I really want to touch on today, at least the things that this project should address. So the first point is that discrete time methods are incredibly popular in the literature. They're pretty much the things that we mostly use, but they may not reflect the underlying theories that we have for how things change. And by contrast, these continuous time methods that exist, and I'll define what these differences are, may be more accurate in reflecting the way that we think about processes, but they're much less used. And in addition to that, just because of the fact that there is more work being done in this discrete time framework, methods for dealing with this idea of undiagnosed heterogeneity in the continuous time framework are likewise even more rare. So we need to address that. And the second point, which I've already kind of touched on, is that researchers are interested in identifying homogeneous subgroups in otherwise heterogeneous samples, right? So I have a ton of people in my data, and I want to think that there are probably groups of people that are more similar to one another than they are to other people in the sample. So if I can find that or otherwise separate out people, then I gain something, right? So if I have the ability to say, okay, there's this specific group of people that have more things in common with one another, then I can actually leverage that shared information that they have to gain more power. And likewise, the inverse is that treating these people, these heterogeneous samples, as a single unit could lead us to spurious associations or missing out on effects that could be there in our data. So let's actually like talk about this. So I'm going to talk about this in like theory land, and then I'm going to move theory land into like equation land, and then we'll kind of like connect those two. So the broad idea is that we have an alignment, or in this case, a misalignment between our theory and our models. And for folks that want to really dig deeper into this, I would really recommend talking to like Rohit Batra, Emilio Ferrer's former grad student, now postdoc, because he has a lot of great ideas about these kinds of timescale-based stuff. So we typically have continuous theories, but we model things in discrete ways. What do I mean by this? So let's imagine that I have some continuously assessed or existing construct like depression. I typically use really sad variables, so I'm just going to kind of stick with depression for the rest of this. But let's say I have some level of depression, and I tend to fluctuate around some baseline of depression. Sometimes I have more depression, sometimes I have less depression, et cetera. And one way of thinking about this is that this depression is persistent. It is always there, whether I'm measuring it or not. And likely, there is probably some temporal sequencing or some serial dependence in my depression. My depression at any given moment is probably related to my depression at other subsequent moments. And that's regardless of whether I'm measuring this or not. In reality, we obviously, one, cannot gather our data at this incredibly finite granularity. And so we have to do basically these red dots, right? So we'll actually measure people realistically. Maybe I kind of just generated this data, so we'll just ignore the time axis. But we'll say maybe every week I assess these people, and then I'll see, okay, this is their depression scores across time. And we can see that the discrete measurements somewhat align with the continuous underlying process, but we're missing some peaks, we're missing some valleys, so there's some information loss. And likewise, you can imagine that I can sample this slower, I can have fewer red dots, I can have more red dots, but these are going to be different, basically realizations of the same underlying process that's presumably always there. And one thing that we typically do, if you're familiar with like these types of time series or autoregressive models, is then we basically connect the dots, right? We'll basically say, does previous dot predict subsequent dot? Basically, we'll do our typical lag one for those that are familiar. For those that are not familiar, we're basically looking at how does one moment typically, on average, predict the next moment. And this type of modeling has a theoretical implication for the actual process that we're modeling. If we're looking at today's effect on tomorrow, we're kind of acting as if nothing happened within that day. Likewise, if I look at this week to next week, I'm still assuming that kind of nothing happened, right? The whole totality of the effect appears the following week. You don't actually exist in between moments. And that's a weird thing, right? We would kind of shrug and say that's a very strange assumption to make, but these models somewhat implicitly suggest that. And so I can make this a little bit maybe more salient by actually using an example. Again, these are psychological symptoms because I'm that type of person. And we can talk about what are the consequences of modeling people discretely, right? And so we can model people. We can model the exact same process. So just some context for this, I'll go into a little bit. But I generated one model, like this kind of continuous time series, this blue line. And I basically sampled the effects at different moments. In the case of what I'll call continuous time models in a little bit, what I call delta t is arbitrary. When I say delta t is 1, it could mean 1 month, it could mean 1 year, really depends on the scale of your data. But for the purposes of this talk, let's just assume that delta t equals 1 corresponds to 1 day, right? So in this case, I have my effects at a daily level. I have my effects every 12 hours. I have my effects every week. And so if I model people at these different sampling rates, I might come up with different conclusions, right? So if I look at the weekly effect of depression on anxiety, effectively, these are almost all zeros, right? So the strongest effect here is a 0.05, and likely that would be very difficult to actually pick up. Alternatively, if I measure someone, let's say at a daily level, I'd see that there's almost a moderate effect of depression predicting anxiety at the next day. It's about 0.27. So this is to say that the association between depression and anxiety depends on when I measure depression and anxiety, right? And this is kind of weird. It would be weird for me to say that, oh, on a weekly level, I'm seeing this effect. On a daily level, I'm seeing this different effect. Sometimes the effects from different studies could disagree solely because we sampled at different moments. And that would be kind of strange. And for the rest of this talk, I'll refer to sampling rate as delta t. So just a change in time, if you want to think about that. To kind of illustrate this point further and kind of motivate this particular project, I'm going to talk about illusory homogeneity. So in this case, I generated two different people. They have different data generating models. They have different values. And I know they're different because I made them up, right? And so I can act like I sampled these people at a 12-hour lag. I can act like I measured them at a 24-hour lag or a 7-day lag. And the actual difference in the magnitude of their effects, I realize it's quite difficult for some people to see. The difference between these two parameters for both people is about like a 0.09, so quite a small difference in these effects. We might be willing to say that these are reasonably similar, right? So when we do like a random effects model, we might say that they are acceptably close to one another to be part of the same group. If I model this at a daily lag, we can see that there's a much more prominent red effect here, a negative association between anxiety and depression, but much weaker for this other individual. So maybe we would start to say, okay, they're certainly pulling apart. They look a little bit more different. But certainly by the weekly level, we would definitely say person 2 is qualitatively different from person 1. There's a very clear negative association here, whereas for this person, they don't look similar at all anymore, right? There's basically no effect. And this is to say that individuals with different true models could appear similar or dissimilar depending on when you sample them, right? So like I'm saying here, if I sample you at a 12-hour interval, you guys look the same, but suddenly at a weekly interval, you look different. And this has the consequence of basically saying that similarity at a specific time scale doesn't actually imply similarity at other timescales. And if we want to ultimately do this, if we want to cluster people because they're the same, presumably same we mean by across all of time. One example that I've kind of toyed with has been this idea of like a depressing event. When something makes us depressed, within like an hour, we're probably less happy. I think that's a fair assumption to make. And the thing that qualitatively separates people with major depression from people with kind of more healthy levels of depression is the association through time, right? So at an hourly level, I would expect most people to look pretty much similar, right? Something upsets you, you become more depressed. But at a weekly level, for typically happen to sample them too quickly, we would now say that the person with major depression looks exactly the same as the person without major depression. And that would be problematic, right? So we don't want our clusters of people to be dependent on when we've sampled them. That would be strange. So I'm going to now connect those concepts to the equations, and we'll do this in a gentle kind of way. So I always tell the grad students in the quant area, but I made this figure. Obviously, this has like UC Davis colors now, but I made this figure in my first year of grad school as a grad student, and I have used this effectively in every single presentation I've ever done. And it's because you do it right the first time and you never have to do it again. So just something that I want to like push of making these figures. So anyway, I'm going to be talking about discrete time modeling of time series data. In this case, the model I'm going to talk about is this vector autoregression. And you can just see pictorially that we have variable 1, variable 2, and they are predicted by variable 1, variable 2 at the prior time step. We usually call this a var1 model. And there are some distinguishing characteristics. You probably picked up on this on the previous slide, but we have the effect of variable 1. Let's call this depression. Depression predicts depression today. So yesterday's depression predicts today's depression, and yesterday's anxiety predicts today's anxiety. These are what we would call the autoregressive effects. And then likewise, yesterday's depression might predict today's anxiety and vice versa. These are our cross regressions. And I'm not really going to go into this. This is just kind of for a more illustrative purpose. But you can basically see this is a regression model, right? You have seen basically linear regression models. This is just how are our scores right now predicted by some intercepts times our regression coefficients matrix. But instead of this being y, instead of x being predicted by y, we have the same variables at the previous moment. Technically speaking, we can extend this to any arbitrary lag. So instead of it being t minus 1, I could do t minus 2, t minus 57, t minus 127. That's totally fine. But for the purpose of this, we'll just stick with lag 1. And I've been talking about this idea of continuous time models, and I'm just going to show the equation for the stochastic differential equation. But before people run, one thing I want to highlight, I usually, when I present these slides, I'm not particularly focused in talking about the equation, but I want you to get an intuition for if you look at this equation and you look at this other equation that I just showed you, you can see very similar elements between these two equations. And it's because they're basically the same thing, except one has calculus, right? Which is scary in and of itself, but it is like a thing, right? So we can say in the discrete time model, we have a discrete step in time. Today is predicted by yesterday. What we see in the stochastic differential equation is actually predicting the differential of eta. This is change, if you want to think of it that way. And so we're saying change in our variables is given by our intercepts, some regression coefficients matrix, and the levels of our variables at the current moment. And you can basically get similar results to this as you approach the limit of time. So if you increasingly shrink t minus 1 to t minus 0.5, t minus 0.001, and you just infinitely get closer to this arbitrary limit of time, you would basically get something similar to the stochastic differential equation. And the reason why this is powerful is because instead of looking at just like a small difference in time, you're looking at the relation between the variable and how it's changing. And so this is more independent of the actual time scale that we're modeling. And so we can compare these models and talk about some limitations. So I've already talked about the idea that these discrete time models have parameters that are dependent on delta t. So whenever you sample, you're going to get different effect sizes. And there's also this thing that I'm not going to go too deep on, but they have a reliance on equally spaced data. So if you look at this equation, it's basically saying today predicted by yesterday. So if you suddenly have a measurement that occurred too late or too early, you're kind of breaking this equation. You can do it, but the math would be weird, right? It's expecting that you have equally spaced data. And generally speaking, you want to fulfill that requirement. So you need equally spaced data, and your parameters are contingent on your sampling rate. I've already kind of touched on this, but continuous time and discrete time models are related by known and well-established transformations. And because of this, we get this unique property that continuous time models can be translated to any discrete time model. So if you have a continuous time model and you're like, I want to see what this effect looks like at the daily level, you can do that. You want to look at what the effect looks like at a weekly level, you can do that. This is all within reason. So obviously, if you're fitting data to like a weekly time series, it'd be weird if you're like, what does this look like at a 10-year level? Because you don't have that much data. So you typically want to extrapolate within reason to whatever your data covers. And so, as I'm kind of mentioning, these continuous models then can be interpreted at different timescales. And they should also be more consistent. So when we're looking at differences between people, we're looking at differences in their differentials or their derivatives, as opposed to some arbitrary step in time. So it becomes less weird, in my opinion. So we can describe this equivalence. I'm just going to kind of like show that you can do it, right? So I can get that discrete time phi at a specific sampling rate by doing the matrix exponential of A times delta t. That's the furthest I'm going to go on this slide, right? So we can just say there is a way to get our regression coefficients matrix in discrete time given a continuous time model. And you can do the same with your process noise covariances. You can basically look at your error covariances and how that changes over time. So I'm going to visually depict this. So in the left column here, we basically have the true continuous time model. And then I basically apply this transformation to look at what the effects look like at a delta t of 1 and a delta t of 10. And what we see is that I have, effects here. They're 0.3, minus 0.3, minus 0.3. For those further back, they can't see these. The dashed lines indicate negative effects. The bold lines mean, or the solid lines mean positive effects, but they're all 0.3. Yes. Yeah. And so when we translate this to a daily level, right? So I want to kind of reiterate that the delta t of 1 is arbitrary. I'm just sticking to a daily interpretation because it's easier for me as well. Weaker effects. So I see there's a lagged effect from variable 1 to variable 2 that's about minus 0.18, right? So there's a weak effect between those two. The other consequence of these transformations is that we see some effects kind of emerge from nowhere, right? Oh, I'm seeing that audio is dropping out on Zoom. I don't know. Hello? Okay. So basically, some effects just kind of appear, right? So we're seeing that this effect from variable 3 to variable 2 and from variable 1 to variable 4 manifest, even though in the true model that wasn't there. And that's because of basically how the matrix exponential transformation works. You're crossing a lot of paths. And so some effects that you observe when you fit these discrete time models are actually indirect effects from your underlying true continuous model. If you want to think about this, your continuous time model is all direct effects. When you fit your lagged model, it might look like a direct effect because there's an arrow there. But implicitly, this is actually a consequence of variable 1 affecting variable 2, affecting variable 4, and it just so happens that over this longer time span, this effect emerges. It's not actually a direct effect now, it's an indirect effect that manifested at the sampling rate. If we then go to a delta t of 10, we can see that for all intents and purposes, these effects are effectively 0, right? So it basically goes from this true model, we can see when effects are more powerful, when effects are more weak. And likewise, with our process noise covariances, we can basically see that from an identity matrix where nothing is related to one another, effects emerge as a function of time. This has some quirks to it that I can talk to about later if anyone's interested, but for the purpose of this, I'm just going to stay focused on the topic. So just to recap, right? So continuous time models probably align a little bit better with our way of thinking about processes. They're things that always exist. They are persistent, whether we think about them or not, whether we measure them or not. And likewise, discrete time methods have several limitations. Their effects depend on that sampling rate. They are affected by unequally spaced measurement occasions, and similarity between people could just be an illusion of the fact that you sampled too quickly or too slowly. So this is the next part where I'm going to finally talk about what the hell undiagnosed heterogeneity means. And so we're going to start with like a broad scope and then again kind of zoom back in, right? So I have this idea of balancing the group and the individual. So models that we use imply something about our assumptions of the real world. When I was in my first year of grad school, one of the faculty members that I worked with talked to me about this idea that if you think about these papers that you read, sometimes it's crazy that everything in the world can be solved with a multi-level model. And that the entire world has kind of molded itself such that it's amenable to that. Or perhaps that maybe we can have more creativity with our models, and that creativity then gives rise to differences in how we can answer questions or ask questions. And so by increasing our methodological tool belt, we necessarily can have a richer, way of kind of interfacing with the world and modeling it. And so apropos to that, our models of the world basically imply assumptions that we're making about it. And so some of these assumptions can be, how much heterogeneity is there in my sample? What is the form of that heterogeneity? So are people continuously different? Is there a spectrum of differences between people, or are there discrete differences? Are there classes of people that behave differently qualitatively? And so there are different things that our models imply about this. And the question becomes, how can we leverage information without placing unnecessarily strict constraints on any particular individual, right? So if we're willing to place the bet that people are largely heterogeneous, but we accept that there are some commonalities in how people change over time, then we want to leverage information when we can, but we don't want to do that to the point that we lose some valuable information regarding people's idiosyncratic behaviors. So I made this figure also in grad school. I call this like an idiothetic spectrum of models. And so we can imagine that on one end, we have these nomothetic models that basically say that everyone is a realization of some single process. Minor differences between individuals are just like noise, essentially. And so we can fit one model to every person, and we're willing to accept that people are, largely homogeneous. At the very extreme end of this, and I come from a school of thought where my own advisor basically published a paper on saying we should do this, is idiographic models, where we're saying every single person is completely unique. There is no association or no expectation that fluctuations or my particular model applies to any other person in this room. And then we have this kind of idiothetic area that I think probably a lot of us are in, where we say probably people have some shared features, but there's also some idiosyncratic features. And you'll find things like your multi-level models, your gimme models, and other things in this area where we're trying to balance how much individual level information we have and how much group level information that we have, right? Because ultimately, it'd be nice if we could model everyone as individuals, but we want to also be able to generalize our results, find common trends or common features that distinguish people from one another. And something that comes up from that is this idea of undiagnosed heterogeneity. So if we imagine that we start here be subgroups or subtypes of individuals. The example that I'll be using has to do with major depressive disorder. And so one can imagine that there are probably people that have subtypes of depression. In fact, just clinically, there are subtypes of depression, right? So we have different types of depression, and we might imagine that phenomenologically, the way that some subtypes of depression manifest is going to be qualitatively or numerically different from other people with major depression. And so we're interested in this idea of identifying subgroups, but as I mentioned earlier, we don't always have a priori knowledge of what makes people different, right? I can have a sample of people with major depression. I can work with people with major depression and pretty easily say that certain people have different ways of expressing their depression over time, but I probably wouldn't be able to put my finger on exactly the feature that distinguishes one set of people from another set of people. And so it would be nice if we can kind of handle this with the magic of statistics and math. And so relating both of these points is that ways of handling this problem, this undiagnosed heterogeneity, exist in the literature, but they're almost all for the discrete time framework. So our s-gimme models, our SCG VAR models, I helped in both of these. ALS VAR models, dynamic mixture models, all of these are currently nested in the discrete time framework. Although I will say that with dynamic mixture models, you can easily extend this to continuous time if you wanted to. But by contrast, very few, if any, methods exist for doing this, identifying clusters of people using continuous time models until now, right? So that's the whole selling point of this talk. And there will now be applause from the audience. So I'm going to talk very briefly about this idea of the group iterative multiple model estimation. It's always like a very big mouthful, but the gimme algorithm. So gimme is a discrete time method that I've mentioned, and it identifies relations between variables that are shared by a majority of people, right? So we basically model people's time series, and we're looking at what features, what pair of variables are connected more often than we would otherwise expect. And in 2017, Katie Gates, along with her grad student Stephanie Lane, published an extension that allows for what we call unsupervised identification of subgroups. It basically uses community detection algorithms to find subgroups of people that share more dynamic features with one another than you would otherwise expect by chance. And more recently, I extended gimme to the continuous time framework. So naturally, it makes sense that I would extend continuous time gimme to also handle this latent heterogeneity that is unobserved. I'm not going to go super deep into this just because of the sake of time, but generally speaking, the way that continuous time gimme works is we estimate the continuous time analog for the var1. So it's the continuous time version of that vector autoregressive model that I showed earlier. It's also the equation for the SDE that I showed earlier. Formally, this is called the Ornstein-Uhlenbeck process. I just have that because I think it sounds cool. And in the past simulation work that we've done, we've found that continuous time gimme outperforms regular gimme in variety of situations, varying effect sizes and varying sampling rates. So whether you sample very slow or very quickly, whether you have strong effects or low effects, continuous time gimme at worst performs exactly the same as regular gimme, and at best performs better. Just to very briefly go into this, the logic of gimme has always been, let's leverage group level information without necessarily constraining a particular person. So what that means is we define what we call a null model. And the null model is basically just a model that everyone is assumed to have at baseline. The null model that we typically use is one where all the autoregressions are freed. So we're basically saying all of your variables are related to all of your other variables in time, but not related to each other. So my depression right now is related to my depression tomorrow, but that's it. There's no connection between my depression and my anxiety. I fit that null model to every single person, and then I assess the modification indices. I basically do a Lagrange multiplier test, and I'm basically looking at the values and saying, which parameter, if I freed up for the most people, would actually improve model fit? And if there is a parameter that would improve the model fit for most people, I add that to everyone's model, right? So the general threshold is between 65 and 75%. So 65 to 75% of people say, I like this path, we should have it, then we add that to every single person. The big thing I'm gonna note is that that added parameter is a flag, right? So I'm just saying, you need this. But whether my x to y is positive or Suryoduti's x to y is negative, there's no constraint on the value. I'm just saying that this seems to be an important connection. And so that's basically what we're doing. We're using information from the whole sample to basically identify what features seem to be important for this group of people. And the extension that we've done is basically now cts-gimme, right? So subgrouping gimme in continuous time. And it's an extension that allows for this unsupervised identification of individuals in heterogeneous time series. And it allows for the estimation as well of subgroup level models as fixed effects. So basically, original gimme at the group level and the subgroup level, you only get structure maps. You basically just see that variables are connected to each other. But now we've added this feature that allows you to actually estimate the model at the level of the subgroup. And in the empirical illustration, it's all output that I'll show you. So you'll be able to, if you choose to use this or you're interested, there will be like a way to kind of follow it as a roadmap. So how do we do this? Well, we use community detection. I'm not going to go too deep into it, but the ultimate idea is that we create an adjacency matrix. It's a matrix that basically just says how many things do people have in common, right? So A is created. We look at paths that we added at the group level, and we also look at modification indices. So we're basically looking at the things we've already added, the things we could add, are people similar in those things, right? And we do a significance test. So the things that you have to be common or similar with another person have to be statistically significant similarities. And then each cell of that adjacency matrix then is just a count of the common features that each person has. This is an example of an adjacency matrix just off of the top of someone's head. How many groups might there be in this matrix? 2, yeah. So you can see that the first 4 people have a lot of things in common, right? And then the last 4 people have a lot of things in common. And then let's say person 1 has nothing in common with person 5, right? So it's very clear in this case, because I simulated these data, it's very clear in this case that there are 2 subgroups, and this is basically the adjacency matrix that continuous time gimme is making. We're counting how many features people have in common, and then we're searching this matrix for groups of people that have more similarities than they do with other people. Obviously, in real life, this is never going to happen. So we have a lot more noise, and we have ways of stabilizing the estimate of the communities that we find. Okay, so recap 2. The selection of a model will imply necessarily something that you believe about the real world. Whether it's explicit or not, these are implicit to the equations that we're using. And while we want to balance group and individual level inference, we want to use group information, we want to use individual level information, we might also be interested in identifying subgroups of data so that we can increase our statistical power and other things. And while many approaches exist for this, until recently, there have been very little attempts to do this in continuous time. So I'm going to talk about basically one motivating question for my simulation study. Currently, a lot of the results for performance of regular continuous time gimme can be found in our research paper that we've published recently. And so this is going to focus mainly on clustering, right? So can we find the real subgroups in simulated data? When I make people up, can I actually find the real differences between people? So I typically don't like slides that have a ton of text, but I have to have this slide. And so I ran a simulation study. This has been something that's been going on for the past month, constantly. It's a very long simulation. But I basically simulate 60 people divided into 3 evenly sized subgroups. They have 6 variables in their time series. I simulate people 100,000 times. And there are the data generating models are at 0.1 resolution. So if you imagine, like roughly every 2 hours, I'm generating data of these people for 100,000 time points. For each group, there are 2 unique features that differentiate them from one another. And those effect sizes at an equivalent delta t of 1 is about 0.2. So these are relatively weak effects that we might often see in psychological research. And kind of, bless you, another point is that the group level model, so every single person actually shares 3 features. So everyone has 3 features, and each subgroup of people have 2 defining characteristics. I then took each subject and I subsampled them from the 100,000 time points at 0.5, so let's say 12 hours, every day and every 5 days. And I subsampled them, I fit both s-gimme and continuous time gimme, and I assessed their cluster quality. So how well do we actually separate people, and does that depend on the sampling rate? And the way I assess this is using the adjusted rand index, or the ARI. The ARI is a unique metric where 0 is still not necessarily the worst you could do. You can actually get a negative value of ARI, but if you get that, then you should be ashamed. But for the ARI, 0 corresponds to chance. That would mean that whatever the frequent or proportions are, you got it right at least that amount of times. Since there's 3 groups, if you get 33% accuracy, you should get an ARI of 0. If you get an ARI of 1, that would be perfect accuracy. And then the generally accepted cutoff is 0.7. So we would say that 0.7 is good enough of a cluster recovery metric. And so these are the figures. The red lines in this case indicate the cutoff for acceptability. The left column is continuous time gimme. The right column is classic gimme, or the s-gimme algorithm. And what we can see is that the averages across these simulations, so this is the average for the continuous time model at a sampling rate of 0.5. It's about 0.61, so it's technically on average unacceptable, but it is substantially closer than the 0.04, right, that you get with discrete time gimme. At a sampling rate of 1, we see that continuous time gimme has a 0.81, which is on average above that threshold of 0.7, whereas for discrete time gimme, it's 0.23 and still well below the threshold. And then at a sampling rate of 5, we're seeing a 0.72, once again, still acceptable on average. But then for discrete time gimme, it's settling at a 0.5. And there's a couple interesting things that we're seeing here, right? There's a relative amount of consistency. I'm not saying that this is consistent, but this is a little bit more stable than certainly the jump from 0.04 to 0.52, which is quite large. But we can also see that regular gimme is getting better as we sample slower. The context of this is that gimme was originally designed to work for modeling heterogeneous fMRI bold signals. And if we think about it, the way that we gather fMRI data, you have the actual scan of the people that's taking place, maybe a picture every 2 seconds. And we're inferring that these pictures are related to brain activity based off of the movement of oxygenated blood. And so you have layers of abstraction and presumably orders of magnitude slower than the process is actually happening. And so the fact that gimme is getting better, if we think about this application to something like fMRI data, I would expect even like 100 times slower, we would probably expect if this trend continues, it should do pretty well, right? But by contrast, continuous time gimme at least seems to be a little more stable. And so this is kind of rehashing these points. In terms of the proportion of Monte Carlo simulations that was above that cutoff, for CT-gimme, it's 31%, 70%, and 48%. Not particularly amazing except for that middle case, but then in terms of S-gimme, the options are 0%, 1.6%, and 20%. So in terms of a comparison, I think it seems pretty evident which one is favorable. So again, CT-gimme is relatively stable across these sampling rates. I don't know if it's much faster or much slower how it'll do. So that's going to be something that we'll continue to test. S-gimme improves as the sampling rate increases. So in a way, sampling slower can be helpful to you. And in some processes, we don't know if we're sampling fast or slow. And so this is kind of the key point here is if you have no idea what the true process is and you're picking a model, presumably you will make a decision here or there. I would imagine that if you for sure feel like you're orders of magnitude slower, maybe the discrete time gimme's clustering would be favorable. But anywhere between 0.5 and 5 times faster or slower to the actual unfolding rate, this would prefer continuous time gimme. Okay, so our actual empirical illustration is a sample of individuals with major depressive disorder. I have obtained this data set from my colleague Omid Ebrahimi at Oxford University. This is a sample of 70 individuals with major depressive disorder. They were assessed on 6 psychological symptoms 5 times a day for 1 month. So roughly 140 time points per person. And so this kind of similarly matches the simulations that I've been conducting because that's why I did it. The items that they were assessed on are anhedonia, depressed mood, lethargy, hunger, irritation, and restlessness. I basically standardized the data within person, and then I fit continuous time gimme. Some of the quirks that you'll see is because we didn't really do data processing. So some people actually have really terrible data, and we could do things to kind of ameliorate that terrible data, and we probably will once we actually publish this. But for like a first pass, we accepted everyone's really, really horrible data. And so if you see weird results, that will probably be the reason why. Okay, so this is going to be both the application of continuous time gimme, but also showing the types of output that you'll get if you choose to use this. So the first thing we get are group level structures. So these are paths that seemingly are important for a majority of people. So we see that in this case, lethargy seems to kind of, I'm going to use quotes, kick off a behavioral cascade. So once lethargy activates, it affects anhedonia, which affects depressed mood, which affects restlessness. And this seems to be apparent for at least a majority of individuals. And then I'm just highlighting here again that these are structural. So these could be positive connections, these could be negative connections, but at least this pathway seems to be important for most of these people. We did the subgrouping, and we see that there are 2 subgroups identified by continuous time gimme. One thing I want to note, I just feel that it's like a responsible thing to do, is that there are a large number of connections between members of the different groups. So this would be something that I would recommend doing like a stability test, right? So it looks like we have 2 subgroups, but it also looks like these are very fragile subgroups of people. And so this is actually the topic of a project that I'll be following up with, looking at fuzzy community detection and integrating that here. For subgroup 1, assuming we can trust the results, we basically see that there's also this characterization of depressed mood affecting irritation and a feedback loop between irritation and hunger. So for this particular set of individuals, depression tends to kick off this spiral or this association between these two things. So when folks get hungry, something happens to their irritation. When they get irritated, something happens to whether they're hungry or not. And that's kick-started by depressed mood. And this is layered on by the group structure that we had of lethargy and these other things. The other thing you get from continuous time gimme's output is this fixed effects model. And what this shows us is actually the association between the variables at an hourly rate, at a 5-hour rate, at a 12-hour rate, and at a daily rate. So we've basically applied those transformations to the continuous time model, and we can see how the relations between the variables change as a function of time. And so what we can see is that at the hourly rate, which I'm gonna pause real quick, at this hourly rate, you can see that everything's dominated by the autoregressions, right? So my depression right now is predicted mostly by my depression an hour ago. But then as I kind of move through, I'm gonna skip to like 1. As I move to a sampling rate of 1 day, we can see that my lethargy is moderately predictive of anhedonia, is predictive of depressed mood, and then that predicts irritation. So when I'm irritated, I tend to be less hungry, but when I'm hungry, I tend to get more irritated. And then this kind of cycle feeds back in on itself. We also get the features of the second subgroup. So in this case, we can see that irritation in this case seems to be the thing that kicks off every other change. So when irritation happens, restlessness happens, anhedonia happens, restlessness goes to depressed mood goes to lethargy. We can again visualize these effects. These effects have the subgroup effects as well as the group level effects. So we're looking at the interplay between both of those. I'm going to just skip again to that daily level. And in this case, we can see that basically depression is a sink. Like a lot of the effects culminate in depression. So irritation affects depression. Irritation affects restlessness, which affects depression. Anhedonia is loosely related to depression. So if we wanted to qualify these individuals, we could say that for one subgroup, depressed mood is an outcome, whereas for this particular group of individuals, it seems like depressed mood is an input variable. It's something that when I get depressed, these other things change as opposed to the opposite. And one thing I want to note is that there's substantial heterogeneity at the person level. So these are just 2 people that I randomly picked. This is a random person from subgroup 1. You can tell from this bidirectional loop. And then this is a random person from subgroup 2. So you can see that other person-specific dynamics appear after we have the group and subgroup level dynamics. So you get all of these from continuous time gimme. So just some general conclusions. So at least based off of our simulation study so far, continuous time gimme tends to outperform classic s-gimme. It doesn't seem to fluctuate quite as much across sampling rates as classic gimme does. The effect sizes, I want to note, are pretty much something that I expect in psychological data, at least for time series data that I've done. These were relatively weak effects, and they're effects that we commonly see. And so in these conditions, it typically outperforms s-gimme. And in our empirical illustration, I don't want to go too deep into this just because the clusters may be unstable, but essentially we're seeing that there seem to be 2 states where depressed mood is either a cause or an outcome. Just some limitations and future directions. The simulation is ongoing, so I was able to pull out the cluster recovery metrics because those are kind of the ones that I'm most interested in right now. But we also have things like varying effect sizes, different subgroup sizes, different sample sizes, et cetera. And then this is going to be a project that I'll be doing with my lab, looking at cluster accuracy with misspecified models. So a criticism that I often have and other people tend to have is that somehow everything in time series is a lag1 model. And so the idea of this project will be to basically look at what if we have different lag orders? What if we just fit the wrong model entirely? Is there robustness to this specific way of clustering people? And just some closing remarks. I just want to thank everyone for your time and actually applauding in that random slide that I had. But also if people have questions, comments, or inquiries, you can email me there. And then this QR code leads to my GitHub, which has the live version of the continuous time gimme code. So if people want to use it, people run into issues. Like those are the things that really help me in terms of programming this out. And that's it. Yeah, thank you.
That was outstanding. Thank you very much. We typically take a student question first. So I want to kick it off. Diego gets a gold star for always being the first student question.
Thanks for the talk. I thought it was very insightful, learning more about the continuous time analyses to look at patterns in the data in the nomothetic and idiographic ways. I was wondering if, well, it reminded me of like latent profile analyses and other analyses that you could, I guess, cluster groups of the sample, but I guess the difference here would be that the powerful thing about this is that it's using autoregressive and showing autoregressive effects and also cross-lagged effects. But I was wondering if this is appropriate to assess causal or make causal inferences, or if it's more focused on just understanding or identifying the system dynamics.
I don't know that this works. Okay, there it is. Hello. So to the first point on like the similarities to latent profile analysis and stuff. So latent profile analysis is just a class of Gaussian mixtures, and there is a relation between Gaussian mixtures and the community detection methods that we're using. So one thing we could do in, where is it? In this step, there's nothing stopping me from changing the way that I do clustering to turn it into something like a Gaussian mixture. So in terms of identifying, in the case of latent profile analysis or just general Gaussian mixtures, you're looking for features that justify the extension of another model, basically. You're enumerating another set of parameters. In those cases, I find that the Gaussian mixtures, so I talked about dynamic mixtures, and that basically uses Gaussians, is that they tend to be somewhat conservative in terms of finding new groups of people. So you're on the right track because people are doing that exact work, but at least in my own experience in fitting those models, it's very hesitant to say that there's another group unless there's dramatic differences between them. Whereas the benefits of this approach of emphasizing minor differences is that we can find those one or two paths that separate people, and it's willing to make that jump more often than the Gaussian class. Your other question was, oh, causal, yes. So this is a tricky question, right? So one way of thinking about this is that if you can fit your continuous time model, the implications of the continuous time associations are that these are direct effects. So in a way, you can talk about causality, but only in the constraints of this is still observational data and there's all these other things. But if you were to talk about causality relative to the vector autoregressive, the discrete time approach, you would have much less ground to stand on, right? So there's a paper by Ryan and Hamacher in 2018 that talks about basically continuous time models and how the continuous time models are basically direct effects and the lagged equivalents are what I was mentioning are indirect effect networks. And so you can, I would recommend basically following up on that paper, but you can basically, you would be more confident, but I would never be 100% confident. Yeah.
Hi, amazing talk. Thank you so much. Going back to how the normal gimme was getting better with the sampling rate increasing, and your example of the bolt, right? And how bolt, there's this lag. So that inspired, like that made me question whether this continuous gimme would be better when we're trying to model behaviors with different paces, such as language and attention, like one is following the other. And so here, all of these variables that you have in your simulation are like these are more like they have similar paces. But if you want to model things at different paces, do you think continuous gimme would have an advantage over the typical gimme?
For the most part, yes. So to the point of gimme getting better as you sample slower, that first part is actually a direct result of this transformation, right? So what is happening here is that as you do this matrix exponential, your lagged effects over a long period of time decay to zero. But then over a long period of time, your process noises accumulate information. So actually, the slower you model, the bigger the effects in your residuals get. And gimme, the discrete time version of gimme, all it does is it structures your residual covariance matrix. And so you're basically picking up on the accumulation of information in the residual process noise. So that's a feature. It's something that one would expect, given that they're fitting the structure of our model. And then to your other question, I don't know why I keep forgetting the second question. What is the second question? Yes. So that would work better with continuous time gimme, right? So the ultimate idea is that we're looking at the relations between our variables and how things are changing. So we're not really interested in their lags, but you would still need a sufficient amount of times where the variables are occurring together, right? So it's very hard to approximate like a derivative for data that are super sparse, but it is possible. And you would have to do some things like rescaling time and stuff, but you could do it. And I think it's the same as my answer to your question as well, is that you would have an easier time doing it with continuous time gimme than you would with discrete time gimme, but it still would be difficult, right? Like if you have orders of magnitude mismatch between the processes, it's something where you're gonna have to think about like how much information am I losing, right? So when I fit the continuous time models, I'm still using these red dots. And so if I don't have sufficient information, it doesn't matter that the method is more powerful because the information just isn't there. Like if I'm sure if I measured this actually like just twice, right, there's not any information there that I can appreciably get. So you still need a sufficient density and a sufficient number of times where those data are occurring together that you would be able to do this. But otherwise you would be able to, yeah.
There's a question on Zoom from Yushan, and I actually had the same question as her, which is how do you determine the sample size for these kinds of analysis? How many participants and time points would you say are generally needed to even begin thinking about such analyses?
Hello, okay. So that's a fantastic question because like, I think when you look up the documentation for discrete time gimme on like Katie's research page on at UNC, the commonly accepted like lower bound criterion is 50 time points. And we've tested continuous time gimme with 50 time points, and I would say that just don't do it. Right? Like in some cases, you have to give up the fact that, yes, I want to have idiosyncratic models and person-specific models, but you ultimately are making a sacrifice of basically, I'm going to capitalize on noise. I'm going to pick up a lot of noise. So in continuous time gimme's case with 50 time points and I think like a 5 variable system, it does at the very lower bound of being okay. In these simulations, I'm using 200 time points, and for a lot of practical reasons, that is sometimes difficult to get. With 100 time points, it can do acceptable, but it scales, right? So if you want to fit continuous time gimme and you have fewer time points, then you need to that you want. But all of it's going to scale and it's going to be like very dynamically weighted where you have to balance out sample size with variables, with time, et cetera. Yeah.
And relatedly, how much variation do you need to have beyond just the number of time points? Because if I sample 200 times within a minute, like but my heart rate isn't going to vary that much over that minute, do you think, there's also like a variance issue that you need to think about before you can use these models?
Yes. The important part of this, and so this actually came up when we were designing continuous time gimme, is that I'm talking about all of these results in the context of like low effect sizes that you would expect to see most of the time. For funsies, we tested a version of continuous time gimme where the dynamics were enormous, but still stable, right? So a lot of these time series analyses rely on this assumption of stationarity, that your mean and covariance structure don't change as a function of time. And what happens is that if you have a nearly explosive time series, so you have a time series that is mathematically never going to explode, but it just kind of meanders instead. So you might imagine that some processes have dynamics that have like really big, almost seasonal looking trends, if I just took 200 time points in a minute, it's going to look like I have an upward linear trend. And now my time series looks explosive, right? So over the long window of time, if we could somehow like zoom out and see the real process, we would know, oh, it's not explosive. But in the sampling frame that we're actually looking at it, it looks explosive, then gimme won't do well. So it's something where we have to have some notion of how the process is unfolding. So it's not per se variability, but it's that you need to have a sufficient sample of the process that you're interested in. If you only get it on the upswing, or if you're only getting it on the downswing, then your dynamics are necessarily an incomplete picture of what's actually going on. Yeah.
Wonderful. Thank you. We are at time, but Dr. Jonathan Park, who, by the way, now has a secondary affiliation to the developmental area, I forgot to say. So we can welcome him as one of our own as well, has a YouTube channel with amazing talks about gimme and other techniques that he uses. So if you want more of Jonathan, you could collaborate with him or check out his talks on his YouTube channel. And let's thank him warmly for coming today. And please give him credit if you use his methods from his YouTube channel. Don't do what some departments do where they use it and don't give him credit.